Saxon Advanced, oh, excuse me, I lost my voice. Saxon Advanced Mathematics, Lesson 13. I made up my own title for this lesson because John sounded really boring. We're going to discuss some interesting tidbits about secants, chords, and tangents. So, properties of circles, properties of lines that are relating to circles, and it's a long lesson. I'm going to focus this lesson on the very practical parts of what you need to know. For each of these properties, John is going to go the extra mile of providing you with a proof to demonstrate that what he's telling us, his interesting tidbits, are verifiable geometric truths. Now, there are two kinds of proofs in this book. Number one is the kind that students are expected to be able to perform themselves, and the second kind are the proofs that John shares so that you know that he's not just fooling around. We're going to focus your efforts on the first kind. You will be working some proofs. We've already started. We're going to keep them super focused on what is manageable. These sort of proofs that are here just so that you know that John is a proper mathematician and can walk his talk. I'm not going to waste your time on them, you guys, because your head is going to be full of many other things, and I want to optimize the space that is available. I promise you there will never be questions about these proofs in your future unless you decide to major in some really obscure branch of geometry, which I don't even know if you can. I mean, you can major in anything, but the average math major even is not going to focus on this. So trust me when I say this is not going to damage your career as a mathematician. All right, let's get to the good stuff. I'm going to show you the facts by demonstrating the way they work in problems. Here's a circle. Here are two what we would call secants, right? They cross through the circle and extend out. They intersect right here. We know that because they're vertical angles, we know that they're going to be the same size, okay? Their intercepted arcs are not necessarily the same size because this is not in the center. Their intersection point is not in the middle of the circle. It's shoved over to the side, so they are of different sizes. What's cool though, whoops, that's supposed to be 40. What's really cool and fun, I think, is that if we know these intercepted arcs, we can find the size of the angle. There's a relationship. Now remember, these aren't inscribed angles like the other ones we've talked about. They're not written on the edge of the circle, like those Teenage Mutant Ninja Turtle mask dudes. These are floating within the middle of the circle. But here's what we do. We take the two intercepted arcs and we find the average of them. So that tells us, whoops, x equals 60 degrees. I don't need to put that there. These are 60-degree angles, which we can deduce by taking the average of the intercepted arcs of the two angles formed by secants, all right? Forget all the fancy words, just understand the picture. This is not in the middle, it's off to the side. We add and divide by 2 to get the size of those angles, all right? And then just so you know what I'm talking about also, here, second my lights, I guess you can see that. Here in the solution, John makes a big thing of showing you the proof of how we can verify that. If you wake up in the middle of the night having nightmares because you can't believe that you can really take the angles of those intersecting secants and their intercepted arcs and find them, here you go. If you ever want to talk about it, let me know. I'm glad to. I just don't want to stuff your mind full of unimportant things because we have so many important things to discuss. Uh-oh. Somehow I got in the middle of some other problems. Moving on. Okay, so that was intersecting secants when they cross in the middle. Now, we have a slightly different scenario, and this is example 13.2. There are 3 different scenarios that they look a little different, but they're all handled the same way. The first one is where we have, these are 2 secants, but notice that they intersect outside of the circle. They're not inscribed. They're not a proper Teenage Mutant Ninja Turtle. The intersection's outside, and then they cross through. Another form of this one, I'll show you how they work, but these all work the same. That's the point I want to make first. This one is a tangent. Ooh, pretend it touches. A tangent and a secant. And the third one is 2 tangents. Hardest one to draw. These all behave the same way, okay? And I'll explain to you. This is 2 secants. This is a secant plus a tangent. And this is 2 tangents. Whoops. Okay, so there are 3 variations, but they all work the same way. Notice in all of these that the point of intersection is outside the circle. Okay, and notice also that in these we have 2 intercepted arcs, right? The angle formed by our lines passes through the circle and creates 2 intercepted arcs. So the way that we find these angles, in every case we're trying to find this angle x. Okay, it's really hard to squeeze those in at this point in my picture, but we're trying to find the size of this angle. What we do before we added the 2 intercepted arcs, when the intersecting point is outside of the circle, we subtract the larger from the smaller. So let's do one, let's put the numbers in so you can see. They're all, no, they're not all the same. Okay, so what I'm giving you now, these are the angle, these are the lengths, the size of the intercepted arcs. So to find angle x here, we would say it's 80 minus 40 divided by 2, or in that case, it's, let's see, 40 over 2, so it would be 20 degrees. All right, for this one, the numbers are slightly different, just to make it interesting. This intercepted arc is 60 degrees, this one is 120. So we'd say x equals 120 minus 60 over 2. That makes it 60 over 2, or 30 degrees. And this one, it's fun because if it's 2 tangents, that means it only actually connects at one point, right? So that means between the larger arc and the smaller arc, we're really covering the whole circle. My red line should extend a little bit more here. Let's make it look better. If this is the point where the tangent touches, and this is the point where the tangent touches, then if I was drawing this with immaculate precision, the larger arc would go all the way up to the dots, and then the smaller one would go all the way to the dots. So that's why our numbers are always going to add. So it would be 260. One second, I'm doing this in a kooky way. 100 over 2. Always dividing by 2. That part is the same. This is our kind of formula, if you will. You don't really have to memorize it if you see the logic of it. All right, and then this one is 260 minus 100 divided by 2 equals 130 divided by 2, which is what, 65? Oh, no, sorry. 260 minus 100 is 160. 160 divided by 2 is 80. I divided by, I don't know what I did. Doesn't matter. All right, so these scenarios involve subtraction. The other one we added. All right. Again, John gets wrapped up in the proofs. Example 13.3 is about proving that. This is the one with the tangents. I don't want you to do the ones that say proof. These are not the kind of proofs we're going to do. So we're skipping down to example 13.5. Again, if we were doing some leisurely course and we had time to study proofs in detail, like I did, I loved proofs when I was in high school because we had a whole class, a whole year on geometry, and most of that time was devoted to proofs, then we could really get into it. But John, we have so much other material to cover in here, and proofs are not important to the greater whole. So that's why I'm running roughshod over some of them. I do kind of wish John would update his book to make it a little more appropriate to what college admissions professionals and standardized testing professionals want to see at this point, because you're never going to get tested. You probably won't even get tested on this in either of those venues. So you're still going to be well prepared. Okay, 13.5. Here is our arc, or our angle rather, that we're interested in. We notice that it's outside of the circle. This is the 30-degree intercepted arc. This is the 80. We subtract, so we've got 80 minus 30 over 2. That's 50. So our answer is 25. Okay? One more of these examples, just to make sure that they're beaten fully into your head. I mean, that sounds painful. You know what I mean. Ingrained, not beaten. We don't need to beat you. Here's our circle. There's a secant, and here is a tangent. Oh, that one's not horrible. There. Okay, so again, we have our intersection outside of the circle. That's important. That tells us whether we're adding or subtracting. This is what we want to learn. It's that little angle there. We know that the larger intercepted arc is 170, and the smaller is 120. Remember that they'll only add up to 360 if it's two tangents. This one is one tangent and one secant, so they don't add up quite the same way. Okay, so our formula is x equals the larger, 170, minus the smaller, 120. The smaller one will always be closer to the angle, and the larger one will always be the one farther away, just because of the way angles are shaped. We divide it by 2, that's 50 over 2, and that tells us that x should be, what did I do wrong? Oh, I see the trick. I see the trick. This 120 isn't that part. The 120 is this part. Oh, look at that. John fooled us. So notice I didn't erase that or rip out the page. I just left it. So we need to know this part But John has told us that the 120 is that part. So what we know is that the whole circle is the 170 plus the 120 plus, let's call it y. This is the part that we need, right? Plus y equals 360. So this time we have to find our own intercepted arc. John's given us information about another part of the circle. But those three should add up to 160. This much is what, 290? So this intercepted arc is 360 minus 90, y equals 70 degrees. So when we do our subtraction, it's x equals 170 minus 70 divided by 2. And that equals 100 over 2. And now we get that x equals 50 degrees. Okay, so tricky little John gave us a different piece of information that we had to use to get the piece that we wanted. I like that. I like when he tricks us. Okay, so there's a whole bunch of problems. Let's go on to another scenario. Notice that in these problems, we weren't talking about the lengths of these segments at all. We were talking about the relationship between the angles and the intercepted arcs. Now we're going to change gears a little bit, and we're going to talk about the chord segments. Let me show you. Pictures are worth a million words. Here we have a circle, and we're not going to make them into secants that run through. We've got chords, right? And we can put letters on them that makes it a little bit easier to talk about them. What these numbers describe is the length of that chord. Okay, so we're breaking this up. How many colors do I have? Not enough. Let me get more colors. So just to be super clear, I'm circling to show that these numbers are the length of the chord that matches their color, okay? And what we see is that if you multiply the two segments of the same chord together, they will be equal to the product of the other two segments multiplied together. Okay, in this case, it's 24 and 24. You multiply them, you don't add them. Isn't that weird? I think that's a weird little thing. Again, John proves it, and that is not of interest to me. What is far more interesting to me are these problems where we take the geometry and we do some algebra with it. That you're much more likely to see that, and you're much more, you're growing your brain in the right ways when you do these application problems. So don't feel like I'm letting you out of the hard part. I'm letting you out of the unimportant part. Okay, so here we have a circle. Ooh, and we have some chords that cross through. Notice they don't cross in the middle. That's not of importance to us. When I draw these pictures, I'm really careful because things get crowded in here when we start drawing all the segment lengths. So I am careful to show which number goes with which segment. Now, this is weird because now we don't have a number, we have an expression. X plus 20. Okay, so do you feel the ground starting to wobble under your feet? All right, so what this means is that we have to take, right, we take the two parts of the same chord, the two segments, and we multiply them together, and they should be equal to the other two sides multiplied together. So 30 times x plus 20 should equal 40 times x plus 10. Let's take a minute and let that soak into your brain. That is not intuitive to me. I would not think that multiplying these would create an equality. That doesn't really resonate in my brain as something that's logical. So I don't know how you feel, but take a second and just let that soak in. And then you'll see that the algebra to solve it is NBD. We distribute 30x plus 600 equals 40x plus 400. We have a decision to make about swimming the fish. We've got X fish and plain number fish. Which way do we want to swim them? I like things to end up positive if possible, so I want to send the 30X this way and the 400 in the opposite direction. Incidentally, over the weekend, I was doing some deep cleaning in my attic, and I came across my middle school yearbook. Oh, yes, I did. And I was so happy, and I frantically started flipping the pages in the front, looking at the faculty members. And yes, my 7th grade algebra teacher, Mr. Jerry Lacrone, has his picture in there. I'm going to bring it to you and show you someday very soon. I don't want to run and get it now, but I have something else that I want to show you. I know I stopped in the middle of this, but it's okay. I'll come back. I found this. Oh my gosh. In high school, I had one class where we had to do index cards for, what did we do them for? Oh, it was for art. Oh, excuse me. Sorry. It was for art and music humanities. And our teacher was very purposeful. She had us organize note cards. So I made a few note cards of other information in other classes that I liked. And look what I found, you guys. These are the laws of logarithms, which are exactly the same as the rules for exponents, only written in log form. And we're going to get to these, I'm not sure, at some point later this fall. I have my note card, and look on the other side. There is the distance equation in almost exactly the form I still like to teach it. And look, y equals mx plus b. You guys, I could not be more excited that I still have, look at my little 7th grade handwriting. Well, no, this was probably later in high school. But I am just beyond pumped that I found this, and I'm so excited. And I wish I had known how to write the rules for exponents the way that I do them now, because it's so much easier to remember. But I'm thrilled that I found this. So I'll be referring to that in the future. That is an heirloom treasure. All right. Unwind back to before I told you about my attic cleaning. We're just solving this. We swam some fish. So now we have 200 equals 10x. Divide both sides by 10, and we get x equals 20. Now, remember that we have taken a geometric situation and we turned it into algebra and we solved it. This number does not represent anything geometric. It doesn't represent the length of one of these segments. It's an algebraic answer. If we want to turn it into an answer about geometry, we have to go back and plug it in. So if we want the length of this segment, we have to plug it in, and we would say that that is 30 units long. And this one, ooh, my arrowhead went crazy. We would say that this one is 40 units long. Okay? So x equals 20 doesn't tell us anything about geometry until we plug it back in. It's the answer John wants. Let me just double check and make sure. Yeah, he says find x. That's all he asks of us. So that's fine, but it's important that you understand the difference between an algebraic value and a geometric value and provide the right answer. All right, more proving. Moving on to, I hate to even say the name of this. Let me draw you a picture. And this is going to be example 1310. Again, John is asking us to work a proof. We're not going to do it. Those are not the right kind of proofs for us. All right, 1310, find x. Now, notice what we have here. We have a secant and a secant. It's almost like a a Teenage Mutant Ninja Turtle headscarf, but he hasn't tied it yet, right? This is like the loose end. He has to tie it in a knot. But it is a secant that has an external part and an internal part. Makes sense, right? This is the part in the circle, that's the part out of the circle. The whole thing is called a secant segment, external, internal. And then the same thing here, secant segment, external, internal. We are not talking about angles at all or intercepted arcs. We're only talking about the segments. And here's what John gives us. Oh, wait. I take that back. I want to do a different example. Okay. Now, when we were inside the circle, we multiplied the two chunks like so. What we're doing out here is even a little trickier. We're multiplying the external part times the total part and setting that equal to the external part, different color, times the total part. That's what will be equal this time. So 3, the external part, times the total part, which we're just gonna call x plus 3 because we don't have a value for that. That is going to be equal to the external part times the whole part. Make sense? Outside times total, those two things will be equal to each other. All right, so now we solve it. And again, this isn't the hard part. The hard part is remembering what the heck you're supposed to do, because everyone always forgets. 3x plus 9 equals, ooh, look at that, x squared plus 3x. Huh. All right, well, for the first time, we've got a kind of a kooky value to deal with, but let's see if we can push this all together and make a quadratic out of it. We have a squared component. We haven't had one yet. All right, let's push everything over to the right and set it to 0, and let's see what we've got. So I'm going to subtract 9, and I'm going to subtract 3x. Oh, that's interesting. Those both cancel. That cancels. And we get, now I'm going to take it and I'm just going to flip it. I'm going to write this part on this side, and then we'll have 0 over here. I'm going to put that on this side. It's x squared minus 9 equals 0. I didn't change any signs. I just wrote it in the opposite order. All right, this is a difference of 2 squares. So that means that x minus 3 times x plus 3 quantity equals 0. We remember that the zero product theorem tells us that if two things are being multiplied together and they equal 0, then either x minus 3 equals 0 or x plus 3 equals 0. That's the only way we can get 0 as a product. So our two possible roots for this problem are x equals 3 or x equals minus 3. And this is the way I like to see the answer. Both of those are boxed as two options, but this is geometry. Is there any way that could be minus 3? No. So we can just eliminate that and show this as our proper answer. All right, so I like to see that you considered the negative one, but that you eliminated it because in geometry, that can't be a negative length. That doesn't make sense. All right, yay. Another proof that we are not going to stick our nose into. And now we're going to do, I want to leave it here. This is example 1312. And I want the picture here so you can see how they compare. Oh my Lord, look at that. Looks like an egg. This time, we have a tangent and a secant segment. And so, let's see, what do we do about that? This, we've still got the external and then the total. We can do that. That looks familiar, right? So it'll be x times x plus 12, right? That's just like here. Let me just show it. It's the external bit times the total bit. But what do we do over on this tangent side? Because the tangent doesn't have anything that goes inside the circle. So you ready what we do? We take this and we square it. We multiply it by itself. So I drew the line there twice. Oh, isn't that weird? That does not seem intuitive to me. So it's times 8 squared. Weird, right? Let's just solve it. Plus 12x equals 64. And then we can subtract the 64 to get it all in one nice trinomial package. Plus 2x, and then it'll be minus 64, right? So we could break out the man-eating dragon, or we could complete this square, but let's just see, hint, hint, if John made this nice enough that we can solve it. Oh, just a second. I wrote 2 instead of 12. I hope that wasn't driving you crazy. When I distributed, it should be 12x, and I just wrote 2x. Let's see if we can solve this by inspection. We're looking for two numbers that multiply to 64, but negative 64, but add to positive 12. All right, so I'm gonna jot down numbers. I'm gonna go up here. If I was doing this not on camera, I would just flip the page and continue on, but I want you to see everything in one place. So I'm gonna go up here and I'm gonna write down pairs of numbers that multiply to minus 64. All right, that could be minus 8 and positive 8. You could switch that, but that adds to 0. That doesn't add to positive 12. Remember, that's the rule. They have to multiply to this and add to that. 32 times 2, or minus 2 and positive 32. That's a difference of negative 30 or positive 30. No. What else? Does 3 go into that? 3 does not. Does 4 go into that? Yeah, 4 goes in. Let's see. Let's just divide it. 64 divided by 4. Once 16. Okay, so it could be minus 16 and positive 4, or it could be minus 4 and positive 16. Aha, that's the difference I want. Because there's the 12. I need this pair, right? Because that gives me the positive 12. So I write in here x minus 4, x plus 16. Remember that if you write those in the other order, it doesn't matter because it's multiplication, and order does not matter in multiplication. And then we would get, using this same 0 factor theorem business that we did here, we would get x equals 4 or x equals negative 16. Again, I would like to see both of those answers, and then I'd like to see the negative one eliminated because that doesn't make sense in a geometry problem. So we get that x equals 4. Yay. All right, that is the end of lesson 13. Let me show you what the problems look like. So here we have secants intersecting in the circle, secants intersecting outside the circle. Then we have chord segments where you multiply one against the other. And then here we have segments of two secants. So it's external piece times the total, external piece times the total. Okay? I don't see one of the tangent versions where you have to square the external part, but that's in your notes as well as in the book. But there shouldn't be any questions requiring you to prove the concepts, the geometric concepts behind that. All right, lesson 13, it's a gem. Understanding how to solve these problems, how to work these problems, may show up on standardized tests. Proving why you can do it that way will not, I promise you. If it doesn't, you can come and tell me off. If you ever discover that in your life, let me know, because I don't want to be a liar. But as far as I understand it, based on my daughter's experience and my previous students' experience, we're good. Okay, lesson 13 is officially done. You guys have been doing a great job of checking in with me, by the way, once a week for our chats. Thank you so much for putting good attention to that and staying on top of it. And I look forward to talking to all three of you this week later on. Okay, goodbye.